Hello, I'm going to be covering Euclid books 7 through 9, and these three books heavily really focused on Greek number theory. So the plan is that we're going to start off with book 7, obviously, and we're going to look at the 22 definitions in that book. And it's really important that we go through them all because to really understand the propositions we're going to do, you have to understand the definitions. Otherwise, I really want to go through them all. I wouldn't spend so much time on them. And then book 8 and 9 don't actually have any definitions, so we're just going to go through some of the propositions of them as well as some of the propositions from book 7. So to get started, like I said, we're going to do the 22 definitions from book 7. So, and these also, as well as I was going to say, they go in groups. So like 1 and 2 go together, and you'll kind of see that as we go along. So starting off, a unit is that by virtue of which each of the things that exist is called one. And so simplified, this is pretty much saying that a unit is one. And we can see that in the picture below as A, right? So A is going to simplify 1. And then for definition 2, a number is a multitude composed of units. So if you look at segment B to E, we can see that B to C is A. It's the same as A, right? So it's going to be 1. And then same goes to C to E, C to D and D to E. So B to E is going to be a number composed of units. And that's what a number is, according to Euclid. And then for definitions 3, 4, and 5, 3 states that a number is a part of a number, the less of the greater, when it measures the greater, right? So if you look at U on A to B, U is a part of that segment because it measures AB. And when he says measures, he pretty much says that U can be multiplied to get AB, right? So a measure is kind of like a divisor. And then these are called parts when it doesn't. So it's going to be a part when it does divide it, but parts when it doesn't. They're really close and it's kind of confused. It's really important not to get part and parts confused even as easily as you could. And then the greater number is a multiple of the less when it is measured by the less. Again, measured being a divisor, you can see that C to F can actually be multiplied by A to B like 2 or 3 times. So the greater number is a multitude actually of AB, so it's a multiple of AB. That kind of just makes sense in our head. And then 6 through 10 are actually really self-explanatory. 6 says that an even number is that which is divisible into 2 equal parts. That's actually really, we know that an even number is 2n according to us, right? 2 times any number. And then an odd number is anything that's not even, right? So it's that which is not divisible into 2 equal parts, or that which differs by a unit from an even number. And this is actually pretty important because differs by a unit means 2n plus 1. So it makes sense with our definition of odd as well. And then 8 says an even times even number is that which is measured by an even number according to an even number. At first, that can sound pretty confusing, but all it really is exactly what the name says. It's even times even number. It's the number which is acquired when you multiply 2 even numbers. And then the same kind of goes for 9 and 10. An even times odd number is the number you acquire when you multiply an even and an odd number. And then same for odd times odd number. And then you can go on to 11 through 14. 11 is a prime number, is that which is measurable by a unit alone. We know what a prime number is. For example, 1, it can only be divided by 7 and 1. So it can only be measured by a unit alone, right? When a unit is, again, 1. So numbers relatively prime are those which are measured by a unit alone as a common measure. So here he's saying that by common measure, he's saying between the 2 numbers, is there a common divisor, right? So we know 2 and 3. The only common divisor between 2 and 3 is going to be 1, right? But if you look at something like 4 and 12, the common divisor between 4 and 12 is 4, right? And that's shown in number 14. Those 2 numbers, 4 and 12, would be relatively composite. And a composite number is that which is measured by another number, right? So like 6 is, can be divided by 2 and 3. So moving on, 15 through 19. A number is said to multiply a number when the latter is added as many times as there are units in the former. Again, at first it can sound really complicated, but pretty much it just defines multiplication, right? So you multiply a number by a number, and then that second number is going to be added as many times as there are units in the former, right? So 2 times 3, you take 3 times 2 units, that'll get you 6, right? So that kind of also just makes sense. And then when 2 planes having multiplied one another make some number, the number produced be called plane. right? So the product of two numbers is going to be called a plane. We see that when we kind of, in a geometrical kind of interpretation of multiplication, if you take two numbers and you multiply them together, you're going to get an area, right? Area here being plane, kind of like the XY plane, and then sides, right? So like the sides of a rectangle are going to be A and B. Again, multiply them together to get your plane or your area. And so those sides are the numbers that you're multiplying together to get your area or plane. 17 says it's pretty much the same thing, but it's three numbers in a solid. So with three numbers having multiplied one another makes some number, the number produced be called solid. And again, it's sides of the numbers which multiply one another. We know this. If you take three numbers, all different, multiplied by each other, you're going to get a rectangular prism. And again, if they're all the same, it's going to be a cube, and that's more of a solid than a plane. We know that. And then a square number is equal multiplied by equal, or a number which is contained by two equal numbers. When he says equal multiplied by equal, he's just saying that you have two numbers, they're going to be the exact same number, you multiply them together, you're going to get a number squared, right? You're going to get that square number. So equal multiplied by equal, just two numbers that are equal to each other multiplied together. And then it's kind of the same for a cube, except it says it's equal multiplied by equal, and again by equal. Again, it sounds weird, but it's really just saying that you're taking three numbers equal to each other, multiply them together, or a number which is contained by three equal numbers, right? We know that. So 20, 21, and 22 didn't go together very well, but definition 20 is really important because it's going to really come up a lot in the next book we look at. So it says numbers are proportional when the first is the same multiple or the same part or the same parts of the second that the third is of the fourth. That's kind of continued proportion kind of idea. But if you're looking at 1 and 2, you know that 1 and 2 are proportional if you can multiply 1 by a number to get 2, right? Whether it's parts, so it's not an even number, or a part when it is, let's say an integer, or the same multiple when it's more than just 1, right? It's more than just that unit. And this really kind of shows it off really well if you're looking at a similar plane and a solid. These are numbers where they're not the same, but they're proportional sides. So if we're looking at this picture here, we have the smaller rectangle has sides 4 and 2, right? If you multiply that by 3 over 2, your top will be 3 and your side will be 6. And that is exactly what we see. So they are proportional to each other. We understand this. And then for 22, a perfect number is that which is equal to the sum of its own parts. This really didn't fit in anywhere else, but it's pretty much just saying that if you have a number and it has parts, right? So it doesn't, it's not measured equally. And then you add them together and you get that number again, it's a perfect number. It's not really used much in any of the propositions. Speaking of that, we're going to move on to our first proposition, proposition 3. I chose 2 propositions from this book that I thought were the most interesting and took everything that would just kind of be combined together to form the best kind of usage of all the definitions. And so if we go through this, we're going to start off by letting A, B, and C be 3 numbers, not all relatively prime, right? So they have a common divisor. That's what we're trying to show them. So we're going to start off with, 3 numbers that have a common divisor. It kind of just makes sense. And so we're going to take the common divisor between A and B. And here he's kind of calling the divisor a measure. It's kind of just, it works to kind of intertwine the two. But we're going to call that number D, right? And then since it's a common measure between A and B, it either will or will not measure C as well. So if it does, then it's a greatest common measure between A, B, and C, right? Since it's a measure between all of them. And if it's not the greatest measure between A, B, and C, then there's some E greater than D such that it measures A, B, and C. And then it's going to also measure D, right? So it's going to also be the greatest common measure for A and B. But that doesn't really make sense considering we just said that D is going to be the greatest common measure. And you can't have 2 greatest common measures. So it's impossible. And so D is going to be the greatest common measure for A, B, and C, right? But then we also have to look at if D doesn't measure C, because it's just the second case of the proof. But when we do, if it doesn't measure C, it's easy to say that C and D are relatively prime, right? Because they're not proportional. There's no measure between the two, right? The only common measure between the two is going to be a unit. So some number is going to measure A, B, and C though, because those aren't relatively prime, right? That's how we started. And so we're going to let E measure D, and then we're going to let D measure A and B, right? Because that's how we had stated earlier. So E must also measure A and B. This is just true because of proportions, right? but then it's also gonna have to measure C, right? Because C is proportional to A and B. So we can say that E is a common measure between A, B, and C. So we can say that E is the greatest common measure. It's the greatest common factor, right? So to continue on, we're going to try and call for contradiction. And so we're going to assume that there exists F such that F is greater than E and F measures A and B, right? F must also measure D since D is the greatest common factor between A, B, and C, right? So F is going to measure A, B, C, and D. So it also must measure E since E is proportional, right? That's not true because we set it up to where it wouldn't, right? So that's impossible. It can and can't not also, measure a number. It's either you do or you don't. So there's no number greater than E that's going to measure A, B, and C. So E has to be the greatest common measure for A, B, and C, right? There's only one. And so that's how you're going to prove that there is one and only one greatest common divisor of three numbers, and that it even exists at all, if those three numbers have it, right? And so moving on, I also wanted to look at Proposition 31 because I personally just really liked it, and it really takes advantage of an infinite proportion, which is actually going to be really important in the next book. So we're going to let A be a composite number, right, to start off this, because what we're looking for to prove is that any composite number is measured by some prime number, right? That kind of just makes sense when we ask ourselves, like, what does that really mean? We're pretty much just saying that any number has a prime divisor, right? So if we're going to let A be composite, then it has to be divided by some prime number. That's what we're going to try and prove. So let's say we're going to call that number B, right? So B can measure A since it's composite. Well, if B is prime, then we're done. That's all we have to show because we're asking for a prime number that measures composite number and we're kind of just done. But if B is also composite, then some number C can measure it, right? We just go on. And by this, C must also measure A. And this is true because if B measures A and C measures B, it's transitive. It's going to be that C measures A as well. So if C is prime, then we're done. And this is true because if C is prime, then it divides the composite number B. And since the composite number B divides A, then C also divides A, right? We kind of just show that since it's proportional. But if C isn't prime, it's composite, then we go again. We say there's a number D that measures C, which also measures A, right? And this just goes on and on and on. You can see in the picture below that it could go on to D, E, F, and it can go on forever, really. And that's kind of just how you show that. The way I kind of looked at it when I was looking at this proof was when we were younger, we did these trees where, like, let's take a number like 40, composite number, and you built trees off of it of what it could be divided by. So 40 could be divided by 4 times 10, right? So you have those two, and you could take the 4 and divide it by, 2 and 2, right? So it's going to be 2 times 2 is 4, and 4 times 10 is, 40. But those numbers are prime, so you're done, right? We showed this proof. And same thing goes for 10. If you were to divide that up into 2 and 5, 5 is prime. You find a prime number that divides, your composite, since 5 divides 40 into, 8 times. So it was really cool because it really showed off how we did that as a kid and how it can become so complicated and like an infinite sequence of times we have to do that. Anyway, off of that tangent, we're going to move on to book 8. Again, there are no definitions. All those were really stated in book 7 that are going to be used in book 7, 8, and 9. But there are 27 propositions. Not going to go all over them. That would take hours and hours and hours. So we're going to go over the thing that I found to be the most interesting, and that is going to be proposition 11. And it is worth stating that all these propositions had to do with proportions and ratios. And I really like this one because when you look at it, it's really complicated, but when you simplify it, like I'll show you in a second here, it's really actually kind of cool. And so it says between two square numbers, there is one mean proportional number, and the square has to the square the duplicate ratio of that which the side has to the side. And when I read that first, I was completely lost, had no idea what it was even trying to say. So when I read it over a few times, the way I kind of understood it was that it says that between two numbers that have been squared, there exists one number that is proportional to both of those numbers, right? So if you took like 2 and 3 and you squared them both, there's a number proportional to both 4 and 9. And also the square's proportion is the same as the ratio between the two sides. So the proportion between the two numbers that you squared, those squares, it's going to be duplicate to the ratio of your sides. And we can show this. So to prove this, we're going to let A and B be square numbers. And then we're going to let C be the side of A and D is the side of B. You can see this in the picture below where A and B are squared numbers and then C and D are the sides, right? So what we're going to try and prove is that between A and B, there's a mean proportional number, and the proportion between A and B is the same ratio as C and D, as you can see in the picture. So we're going to multiply C and D to get E, right? And just have that kind of like in the side to know that we have it, right? So multiply C and D to get E. We know that C multiplied by itself gives us A, and D multiplied by itself gives us B. This is just by definition a square. We know that. And so by these two facts, we know that C is to D as A is to E. And this is true by multiplication and proportions. And then for the same reason, C is to D as E is to B. Exact same reason. If you go and you look at the two proportions, it kind of makes sense when you look at the two side by side, like A is to D and C is to D as A is to E, and then C is to D as E is to B. If you look at this too, it makes sense if you don't already understand it. And so by those two proportions, we could see that A is to E and E is to B. And if you notice, that's actually exactly the first part of the proof, right? Because we've shown that that proportion is identical, right? We've shown that there exists a mean proportional number to A and B, which is really cool. And the number is going to be E. It's actually, your two sides multiplied together. And so now we're going to show that the square's proportion is the same as the ratio between the two sides. And so we're going to let A, B, and E all share a proportion. Again, that's just true. We know that since we showed that in the last proof. And so we can say that the ratio between A to B is identical between the ratio to A to E. And we showed in last proof that A is to E as C is to D. And by these two facts, we can know that the ratio between A to B is the same as the ratio between C to D, right? And again, that's just kind of by proportion. And so we're just kind of done at that point. We know that the proportions are identical. We know that there exists a number that is an identical proportion, a mean proportion between the two squared numbers. So that's proposition 11. And then we get on to book 9. This was a lot to do with self-multiplication. And by that, I mean, like x times x is going to be x squared, x times x is cubed, and so on and so forth. An infinite proportion. So it's kind of like taking book 8 and being like, well, we can do this forever. We could take these proportions and keep going and going and going and going and going. And it's going to be the exact same throughout. And so what I tried to do is I looked through all the propositions, and I actually kind of found one that took both of these properties, self-multiplication and infinite proportions, and combined it into one proof. And I really like it. And that's going to be proposition 9. And it pretty much says, if as many numbers as we please, beginning from a unit, are in continued proportion, and the number after the unit is a square, then all the rest are also square. So it's pretty much saying if A is after the unit and A is a square, then B, C, D, E, and F, if they're in a continued proportion, they're also all going to be squares, right? And we see that with x squared. It's going to be, if it's continued proportion, you're going to see that they're all squares. They have to be, right? So like 2 times 2 is going to be 4, 3 times 3 is going to be 9. And it seems really simple when you think about it. You just think of x squared, and we just kind of know that to be x squared, right? We're just kind of like, that just kind of makes sense. But how do we know that makes sense is what he's trying to prove here. So let's those 6 numbers that I just listed, let's just let them exist. And we're going to let A be the number after the unit, like I said, and we're going to let A be squared, right? So kind of just ignore those last 5 numbers for now. And so we're trying to prove that the rest of them are also squares. And since the unit is to A as A is to B, since the unit measures A as many times as A measures B, since A is proportional to the unit, because that's kind of just how he sets it up, A multiplied by A therefore has to be B, right? It's a square of A, right? And then this can be continued on to show that the rest of them are square as well. So it's kind of simple, but it can be like continued on to show that since the unit is to A as A is to B, A times A has to be B, since the unit squared is going to give us A. And it has to be the continued proportion as he states. Therefore, B times B is going to be C. And C times C is going to have to be D. And then D squared E squared is going to be F, and so on and so forth infinitely. And so we want to show it for cubics. And to show that, We have to acknowledge that the unit measures A as many times as B, right? As many times as A measures B, right? So if A is going to measure, I mean, if the unit measures A X amount of times, then that's how many times A is going to measure B, since it's the square of A, right? That kind of just makes sense. If you had A squared to give, I mean, unit squared to give you A, and then it's that continued proportion, A squared is going to have to give you B, and that's the same amount of times as the unit was to give you A, right? So, um, since the unit measures A, B measures C in terms of that unit. And by that, he's pretty much saying exactly kind of what I told you, is that you're going to use that unit back down to A to prove that, unit squared is going to give you A squared is going to give you B squared is going to give you C. But in this term, it's going to be cubic, right? So it's going to be 3. It's going to be 3 times. 3 cubics gives you the A, and then 3 the A is going to give you B, right? And so this can be go on, forever again, just like you did with the squares, up until, however many letters of the alphabet right? And so since the sequence kind of makes sense and that the continued proportion is shown to be cubic all throughout all of our numbers, then it shows that the infinite proportion is going to be the exact same, as long as, and it's really important that it is a continued proportion, right? If you get off of that proportion at any point, then those numbers aren't going to be cubic anymore. They're not going to be squared anymore. You have to continue on that exact proportion, right? It kind of makes sense. Like if we were to, diverge off of x squared, it really wouldn't, that continued proportion really wouldn't make sense anymore, right? So that's all I have for you today. I really appreciate it. And yeah, thank you.